Welcome to Usability and Human Factors Approaches to Design. This is Lecture B. In today's lectures, our objectives include describing requirements analysis and cognitive task analysis, characterizing the role of prototypes in design, and describe the principles of participatory design. The lecture will focus on the role of prototypes. It is expected that you should be able to explain the difference between low-fidelity and high-fidelity prototypes, and when it would be appropriate to use one versus the other. Requirements are a set of activities that are undertaken prior to the design process or early in the design cycle. Requirements can be defined in the following ways: an explanation of what the system should be or should do, which is very basic to the design process. Requirements may be in the form of documentation of needs in order to communicate between everyone involved in system development. They also reflect a set of goals that define objectives for design. We can also answer the question of what are we trying to achieve? There are basically two aims. The first is to identify needs so that the system can support the user's goals. The second is to produce a set of stable requirements that can be moved forward into the design activity. This slide elaborates on some of the reasons for design requirements. We want to make communication clear, unambiguous, and specific on system needs. This clarity of communication is important at the level of interaction with the client or intended community of users and among the development team. Other reasons include the need to identify potential mismatch between user needs and designers' understanding. Such mismatches are a source of significant usability problems and great end-user frustrations. Although requirements engineering can be time-intensive, it can save significant amounts of time, effort, and costs downstream. Once you are well into the development cycle or once a product is finished, changes to it are far more costly. The flip side is that you live with compromises that are not very satisfying. Generating scenarios of use are useful for understanding the ways in which systems can be used and how they will interact with the user. A use case in software engineering is a description of a system's behavior as it responds to a request that originates from outside of that system. Usability.gov describes a use case this way. It outlines from a user's point of view a system's behavior as it responds to a request. Each use case is represented as a sequence of simple steps, beginning with a user's goal and ending when that goal is fulfilled. Use cases add value because they help explain how the system should behave, and in the process, they also help brainstorm what could go wrong. They provide a list of goals, and this list can be used to establish the cost and complexity of the system. Project teams can then negotiate which functions become requirements and are built. The use case method is used to capture a system's behavioral requirements by detailing scenario-driven threads through the functional requirements. Clinical information systems include tasks of data retrieval and entry, requesting laboratory tests or X-rays, billing for services, and so forth. Task analysis names a family of methods which details how something is accomplished, typically in a work setting. Identifying the tasks a system will support and how it will do so are important aspects of design. Cognitive task analysis, CTA, is a task analytic method for describing knowledge and strategies required for task performance. Every task can be broken down into subtasks and further decomposed into particular steps, which may be behavioral or cognitive and involve an inference or conclusion. We will illustrate such an analysis in a minute. The objective is to yield information about the knowledge, thought process, and goal structures that underlie observable task performance. This is best illustrated in terms of a relatively simple and familiar task of getting cash from an automatic teller machine or ATM. We can start by defining a set of steps and conditions that are needed to satisfy the steps. They are expressed as procedures or if-then statements. If one follows these procedures in sequence, then the goal of securing cash should be achieved. The first procedure merely indicates that an ATM is available. Then one's card should be inserted in the appropriate slot. These are a relatively simple set of procedures, but tasks may involve many more steps. Breaking down a task into steps or procedures is very helpful in understanding its complexity. This slide and the next show a walkthrough analysis of securing cash from an ATM. In this method, we code goals, actions, and system responses. If we are designing a system, we would have to anticipate the system response. Goals can be further divided into sub-goals. The analysis includes 7 actions and requires traversing 7 distinct screens. In this case, each system response brings up another screen. It's useful to walk through this exercise on your own, or think through an analysis of another ATM task, such as depositing a check or paying one's credit card. Prototypes are an embodiment of a set of design concepts. It is central to all design disciplines. It is an artifact used to facilitate team communication and is used to communicate to stakeholders and end users. Prototypes can be used to answer questions and support designers in choosing between alternative conceptualizations. Prototypes can be subjected to usability evaluation and contribute to iterative design. We can distinguish between low-fidelity prototypes, which may be a pencil and paper mock-up, to high-fidelity ones, which may embody many of the same functions in a particular interface. Prototype displays and/or functions can be expressed as storyboards. Low-fidelity prototypes can be produced quickly and cheaply. They can be used to elicit user participation. Basic usability evaluation can be done on paper prototypes or storyboards. Low-fidelity prototypes can be discarded when they are no longer needed. A couple of problems are that it is hard to convey flow, as in a program workflow, and is even harder to convert to code. They are underspecified in terms of functional details. However, they can be extremely useful nonetheless. The IdeaTel project was a large-scale, home-based telemedicine project for medically underserved diabetic patients who were older adults. The project was confronted with significant challenges given the population was largely new to computing and had lower literacy. The system had to support multiple functions with minimal demands. The notion of a hardware launchpad provides a physical, tangible device that could be used as a kind of control center. For example, users could hit the green button to connect via video to a nurse, hit the yellow button to their blood glucose values, and access the web by pressing the blue button. This picture shows crude-looking paper sketch or mock-up of the design. The interesting thing is that it captured the essence of the design and it mapped really well to a functioning system. This is a high-fidelity mock-up prototype of a nascent system designed for scientists working in the field of autism. This system is a collaborative effort between the Simons Foundation and Prometheus Research. The tool provides users with access to a large database with extensive phenotypic and genomic information on autistic children and families. The high-fidelity mock-up was assembled with a diagramming visualization tool. The interface approximates a final design. The screen is partitioned into areas that support different functionality. It anticipates the structure of user interaction, dialogue, and mirrors the workflow on paper. The prototype mock-up design was informed by usability testing and requirements analysis on related projects. PicDiv Plastic Interface for Collaborative Technology Initiative through Video Exploration, is a participatory design technique for eliciting ideas. It is done with paper on different colors, scissors, pens, and post-it notes. It is a very useful low-cost approach for generating design concepts and trying to map various system functions on a display or set of displays. High-fidelity prototyping involves the use of software to design a system that manifests some degree of functionality and interactivity. A high-fidelity prototype enables the kind of collaboration between product manager, interaction designer, and architect-engineer that is necessary to create a valuable, useful, and feasible product. The prototype may be nothing more than interim work product to be discarded when no longer needed, or it may actually be reused by software engineers. This table is rather self-explanatory. There are clear advantages to low-fidelity prototyping, such as low costs and the ability to do multiple designs. The disadvantages include the lack of detailed specifications to be used in design and navigational limitations. High-fidelity prototypes more closely resemble a final product and can offer a glimpse into system functionality. On the other hand, it involves an expensive and time-consuming process. Participatory design extends the concept of user-centered design towards fully engaging users and other stakeholders, e.g., management, in the design process. This means more than the soliciting opinions or using users to evaluate a product. Historically, participatory design, which is rooted in Scandinavian design movement, embraces the philosophy of democratization and empowerment. A core concept is that every stakeholder has a voice, not just the people who hold positions of power. There is a recognition that the use of products stretch beyond their conventional or intended range of application. Workers are a prime source of innovation and can learn much by observing their practices. Systems do not merely refer to what is contained in a computer box or even in a wired network of such boxes. Rather, systems are networks of people, practices, and technology embedded in particular organizational contexts. Designers who embrace this philosophy also view technology as a means to improve the lives of workers. For example, it could reduce tedium associated with work tasks, design new opportunities for exercising creativity, and allow for increased worker control over work content. We are going to discuss a case study in participatory design. This involves an application known as SysOM. It's an application developed by Dr. Cornelia Ruland and colleagues in Oslo, Norway. It is designed to support children with cancer, giving them a voice to express their problems. Childhood cancer is associated with multiple physical, psychosocial, and behavioral symptoms and problems. Treatment usually involves multiple hospitalizations and interference with the child's normal development. Children are particularly vulnerable because they lack the personal resources or life experience to cope with the illness and have limited verbal skills to communicate their problems that therefore are often underdiagnosed and undertreated. As a result, Ruland and colleagues developed a communication tool to help children with cancer ages 7 through 12 communicate their symptoms and problems, thereby giving them a voice. It also improved communication between the child, parents, and healthcare providers while assisting healthcare providers in individually tailored patient care. Developing an application for seriously ill children poses a number of specific design challenges. Children have different perceptions of the world than adults. Smaller children cannot read fluently. Therefore, a system needs to be adjusted to children's cognitive and emotional developmental stage. It should allow children to understand and navigate the system without being able to read or write. Given the serious nature of cancer, it should balance an engaging, child-friendly interface with something that mirrors the solemn nature of the task. It needs to not be too demanding cognitively or emotionally. It should also provide a sense of mastery and accomplishment. Both healthy children and those suffering from cancer were invited to participate in the design process. They contributed to the design of the graphical user interface by selecting understandable, child-friendly terms, creating appropriate graphical representations, and improving the usability for this population. The healthy children were recruited from a local school for sessions that lasted 2 hours. They engaged in sets of activity, including the development of scenarios. The children also brainstormed about possible design concepts and developed low-fidelity prototypes. Some of the sessions were led by a graphic designer who drew out children's ideas, and they also served as a sounding board for various design ideas. The sessions were videotaped. This is a picture of a design session with 3 young girls, the graphic designer and project leader. Children were read a scenario about a child that was sick and had to go to the hospital. Children were asked to role-play what these symptoms felt like. The children were then asked to start designing a system based on the scenario they had just heard, draw or build what it could look like and how it would behave. Children were provided with a large table equipped with low-tech prototype material, including paper in different colors, crayons, pencils, cardboard, etc., and asked to work on the task in groups of 2 to 3. Towards the end of each session, each subgroup was asked to summarize their ideas to the rest of the group that provided feedback. Of course, children are not professional designers or developers. They concede valuable ideas, but these ideas have to be balanced with constraints, such as system requirements, usability criteria, usability heuristics, and interface guidelines. We will further explore usability heuristics later in this unit. One design idea that emerged from the sessions was a sailing from island to island navigation theme. The children suggested that symptoms be placed on islands and that the sick children can sail from place to place in order to select symptoms. Also, that each child could create the main character and arrange its appearance by choosing among attributes such as hair and clothes. This picture illustrates an island with different physical symptoms. The My Body Island provides resources for children to explain their concerns about pain, feelings, or any source of discomfort, including one's appearance. Children were encouraged to use a pencil to paint on the body where it hurts, bleeds, or itches. If they select pain and discomfort, they can select either bleeding and bruises, hurting, or itching. Using the paintbrush, they can identify the specific locations on their body which are bothering them. Children were able to contribute very useful ideas that the adult designers would not have thought of and that considerably improved the software. It was also crucial that they participated in evaluations of the system. However, it is important to keep in mind that they are not professional designers and do not always have a sound grasp of logical design. Good design for ill children requires knowledge, skills, and pedagogical and psychological insights children don't have. In general, participatory design by name engenders serious participation of users and stakeholders. Although their ideas are taken seriously, professional designers are needed to give ideas shape and select those that are most productive and feasible. This concludes Lecture B of Usability and Human Factors Approaches to Design. In summary, this lecture characterized the goals of a requirements analysis. We also demonstrated a cognitive task analysis using the task of securing funds from an ATM as an example. The lecture also characterized the role of prototypes in design and explained the difference between low-fidelity and high-fidelity prototypes. A focal point of the lecture was a detailed case study of participatory design that employed children to help develop a tool for children with cancer. The case study demonstrated the role that participatory design can play in the design process. In the next lecture, we will focus on design principles to support usability and particularly on Nielsen's heuristics and their role in design.